So today we're going to look at quadratic drag. And just as a reminder, quadratic drag is equal to negative c v squared v hat, which is negative c v and our vector. So what can we do with this? How are we going to derive these equations? So I'm going to use this familiar notation again. X dot is equal to v. So we're only going to consider horizontal motion. So we're only going to consider motion in the x. We're going to do Newton's law, second law, F, the total forces, equals m times x dot, which is, well, we only have one force. So c times the magnitude of x dot, which I'm actually just going to call v, times x dot, right? So actually, better yet, I'm just going to actually call this x dot squared, since that's really all it is, right? So this is a differential equation, once again. Well, how are we going to do this? Well, we're going to do this like before. X double dot over x dot. We can use x dot squared. We can use separation of variables minus c over m. And I'm going to use this simplification, tau equals m over c, for this is the quadratic drag, right? And what do we get? Well, we integrate both sides. We're going to integrate, this is a function of s, ds, from 0 to t, and 0 to t of ds. Well, what's going to come out of that? Well, we're going to get 1 over x dot, 1 over x dot at 0 minus this, which is going to be equal to minus c over m times time, right? So after we do that, well, we can move sides around. We get, I'm going to call this v naught. So we want to move stuff around. We get 1 over x dot is equal to 1 over v naught, so we move this to the side, plus c over m times time. And so what do? We want to, this is a fraction, we want to multiply both sides by common factors, m plus c v naught t over v naught times m. Yes, and that should give us that fraction. So that's, and then all you want to do, well, you want to swap that the reciprocal, so that's v naught over m, v naught times m over m plus c m, or c v naught t. And now I'm going to use this substitution for t. This is for tau, sorry, it's going to be v naught. So if we divide by m, we get 1 plus tau, or plus v naught over tau times time. Or, yes. So interesting equation. And actually, I lied here a little bit. This is going to be c v naught, so we can ignore this v naught term, or c v naught, so that we can actually erase this v naught, and we can just put a 1 times tau. Right. So, what can we do with this now? Well, we want to integrate once more. So we do the same thing as we did up here. Get x minus x naught is going to be equal to, and then this is a logarithm. So we're going to get v naught times the natural log of 1 plus t over tau. And then that should be it. If you do the same thing from 0 to t, you'll find that, okay, we got the first value is t, then we subtract, and then this becomes natural log of 1, which is 0. So we don't have to worry about that. And so our final equation of motion with quadratic drag in the x direction is x is equal to x naught plus our initial velocity natural log 1 plus t over tau. And that's our linear term. Let's look at these graphs. Plot these graphs quickly. This is going to be our v naught. And this time, v naught, as t approaches infinity, this approaches 0. Okay, as we'd expect. So this is going to be infinity, and this is going to be time. Now, if we had our other graph of x over time, this time we're not bounded by x, so we start at x naught, and this is going to basically grow to infinity, because natural log of infinity is infinity. So t, and there's infinity, grows to x infinity. So those are our graphs. That's derivation. Next we're going to be looking at vertical motion with quadratic drag.